Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is part 317 of this series of streams in which I am developing a new open source app called Notestrator that allows you to draw on top of your screen, and I'm developing that using Electron, so we are using HTML, CSS, and JavaScript. And for today's session, I have a guest. Hi, David. How are you doing?
Hello, very well. Excited to be here.
Thank you for joining me. And I guess you know that the thing that we are going to do today is kind of writing some real code backed by mathematics. We're going to implement some mathematical functions here. And that's why you're interested, right? That's why you wanted to join today.
Exactly. I'm excited to put you through it.
Yeah, so we are doing this app, and let's start running the app. And the intent of this app is that you will have one of these tablets, and maybe you are streaming, maybe you are an educator and you have some people on office hours or some lectures of some kind, and you are maybe writing some code and you want to be able to draw on top of your screen to highlight something and to draw arrows between things and so forth. But note how the lines are not smooth, especially if I am very fast in my drawing, then the lines are not smooth. And the reason is that we are starting to draw the line when you click, because when you put the pen on the tablet, it is equivalent to clicking. And then when you move the cursor, I detect a bunch of on-mouse move events, and I draw lines between the positions, which is not fast enough for the line to be smooth. As you can see, one event fired here and the next one fired here, or vice versa. I don't remember the order, but I don't remember if I was drawing in this direction or the other. But the problem is that the on-mouse move events don't fire often enough for the curve to be smooth. So yesterday I tried, not yesterday, the day before that, on Monday, I tried one smoothing algorithm that was super naive and it failed miserably. But since then, I read more about smoothing and about Bezier curves, and I figured what I think will be a good solution. So what we're going to do today is to implement this solution and see how it goes. So just briefly, the thing that I did before was I looked at path, this SVG element that takes its argument. It's probably the most general SVG element, and it doesn't take a collection of points. No, it takes this path definition, and in this definition you can do a bunch of operations. So you can move the cursor somewhere, or you can draw lines. So you could use path, this SVG element, to do exactly what we are doing, but we are doing it with a simpler SVG element called a polyline, and that just literally draws lines between points. But the advantage of using path over polyline is that it gives us Bezier curves, and these are lines that are not straight. They are curvy lines. And there are different ways of specifying Bezier curves. There are cubic Bezier curves, quadratic Bezier curves. There are even elliptical curves, elliptical arc curves. So path is much more powerful, but the problem is that I didn't know how to use it. So I looked at all the possibilities here, and I knew that I wanted something that was curvy. So I looked at all these three options, and I found one. So look at how naive this is. So I found one that didn't require any extra points. It was this one. So I tried it, but it didn't work. And the problem is that if you don't provide any extra points besides the points that you are drawing, the curve depends on extra points. You need these extra handles called control points. But if you don't provide control points, then the best that the mathematics behind this can do is try to guess the points for you, which is good if you want a line that looks like this, ziggy-zagging, but that's not what we want. We just want to smooth whatever you drew. So by using this kind of curve, what you had was one of those squiggly lines, which is kind of fun, but not what we want. So I did some reading to learn more about Bezier curves and to learn about how to compute these extra points we need. These are not points on the line that we want to draw. These are points that are called control points and determine how curvy the curve will be. So we will need to write some code to do the calculations for the coordinates of these points, these so-called control points. And we'll not use the kind of curve that I was trying to use, the quadratic Bezier curve from a current point. What we are going to do is a full-blown, very traditional cubic Bezier curve. So we're going to learn about how Bezier curves actually work and how to compute these points. So what we currently have is just a bunch of points, and I'm drawing straight lines between the points. And we will want to make these lines curvy, so we will compute these points, these control points. And to show the idea behind this calculation, here is a vector drawing program. So in this program, we can play around with Bezier curves. The program is Inkscape, by the way. If you want to install Inkscape, it is free and open source. Have you used one of these programs before, David?
I used Inkscape many years ago, but yeah, haven't done since. I did look at a few examples of how cubic and quadratic Bezier curves work, but not using something like Inkscape. So curious to see how it shows that.
Yeah, so Inkscape is like Illustrator for those who know Illustrator but don't know Inkscape. The difference is that Inkscape is open source. So one of the tools is to draw Bezier curves and straight lines. So to begin with, we can do something similar to what we are doing now in our app, which is to just draw some points, and then this will draw lines between the points like this. So that's what we currently have in the app. And what we want to do is to smooth this out, because the points are not so far apart and crazy like that unless you can do super fast movement. What we have is more like this. And then what we would like is to not change the points. We will not try to take points away and do something called simplification, which is something that Inkscape can do. If you have a path, then it is possible to simplify this path. Well, maybe I have to select the points in the path.
This is bringing back memories. I have used this.
I don't know. Maybe I have to make the points curvy and then I can simplify the path. There you go. There you go. So I can simplify this path, and I'm doing this over and over, and now the path is so simple that it is a single curve. So that is something we talked about on Monday. It is something that we can do, and there are even libraries for this, and there is a paper that we could read and implement. But we are not in that business. We don't want to necessarily remove the points and make the curve or make the line simpler. What we are interested in is just making the line curvy between the points that were collected on the onMouseMove event. So let's look at, so this is our path. This is the thing that you drew by moving around in our app.
Mm-hmm.
Let's zoom in and really understand what one of these segments will look like. So I'll get rid of all the other points, and we'll zoom into what a single segment looks like. So currently it's a line, but we want to make it curvy. So now we made it curvy, and we can see that one of these Bézier segments is controlled by 4 points. These 2 points are the points that you drew. So those are the points that we don't want to change. We don't want to remove or move them around. And these are the so-called control points, these 2 points up here. These are the points that we will need to compute. We are not just getting them from your cursor position. And they determine how curvy the curve will be. So if I put the control points very near, close to the main points, then the curve is not curvy. On the other hand, if I move these control points further away from the main points, then the curve is very curvy. And
Makes sense.
yeah, and I was trying to find a magic way of determining these points, but the problem is there is no magic. You have to tell the program how curvy you want your curves to be. Do you want them to be close to straight lines, or do you want them to be super curvy and even drawing loops around these points, which is something that if you have a curve that is very curvy, it will start to loop around. So,
Do you have? Is it able to demonstrate the difference between a cubic and a quadratic Bezier curve?
I think that that is possible, and I think that there are different kinds of nodes here, and I think that in some of these nodes, if we make these nodes different, then maybe it will not be a cubic, but it will be quadratic. I guess I'm wrong. I guess the only possibilities are straight line or cubic Bezier curves, at least in Inkscape.
Okay.
Yeah, so it seems like you can only make straight lines
From my
or curves.
understanding, this is a cubic Bezier curve, and a quadratic one, like if I had to oversimplify it, only has one control point, whereas this one has two.
Yeah, so I guess if we do it like this, where we just make the 2 points meet, then this will behave like a quadratic Bezier curve. I guess it's quadratic because there are two of these lines.
Yeah.
And then here you can think of these as 3 lines. 1, 2, and an implicit line between these 2 control points. And if you look for this, I did some research on this, and you start looking for information about Bezier curves, what most materials are going to teach you is how to, given the 4 control points, how to draw this, how to do the thing that Inkscape is doing for us.
Yeah.
But we're not interested in that because SVGs are already capable of drawing the curve. If I just tell it the control points, the SVG is going to draw this for me. In fact, Inkscape is based on SVG, so this is an SVG. We can go here to the source and look at the path, and we will see one of those D parameters with move the cursor to this position and then draw a cubic Bezier curve with these control points and so forth. So I wanted to use Inkscape because it is free and you can play around with it if you don't want to pay Adobe for an Illustrator license, but also because we can see the SVG underneath and we can use it to learn more and play around.
Yeah, that's a really good way of demoing it, actually.
So now we are in this business of, we don't really want to learn how to draw Bezier curves, and we are not really interested in understanding how the Bezier curves work. What we are interested in is how to find the control points and given a bunch of line segments, right? That is our challenge.
Yeah.
So to explain, I said that most materials will teach you how to draw the Bezier curve, which is not what we want. We are interested in finding the control points. And I found this page, which is linked below. And on this page, there is an algorithm that seems to be the simplest and the one that most people talk about. Because if you try to do this search, you're going to find many places where they are doing derivations of algorithms and complicated mathematics with matrices, and it went way over my head. But this one is simple, and it has an intuition that is geometric. So that's the one we are going to use, and we'll see if it's good enough. And we are going to implement this from scratch. We are not going to use any libraries. We're just going to use the idea behind this web page. So let me explain the idea so that you don't have to read the web page. It goes like this. So let's look at not a single segment. Let's look at 2 segments. Like so. So these 2 segments have, here you will have 2 control points, and over here 2 more control points. Okay? So what this algorithm is going to do is it's going to compute these 2 control points in the middle. So it's going to compute the right-hand side of the first line segment and the left-hand side of the second segment. So we will have to iterate on this to actually compute all the control points for all the line segments. But let's zoom into this case and talk about how we want to compute these 2 control points. So only these two. Forget about these other ones. They will be, so we are going to iterate on the curve or iterate on the sequence of points, and this will be computed when we look at the next line segment that I don't even have it on the screen. Okay? Does that make sense?
Got it. Yeah. So you always calculate either side of a particular point, and yeah, that way they will get covered eventually.
Which is a fine way of reasoning about Bezier curves, even though if you really want to be precise about the drawing process, you want to talk about a line segment, but to reason about the curve, it makes more sense to talk about the nodes and how the nodes are in relation to the rest of the figure. In fact, that is the presentation that Inkscape gives us, and I bet that Illustrator is just like this, and many other drawing apps will be like this. So I can talk about line segments and make them straight or curvy, but I can also talk about the points. So I can say that this point is a kind of point that is it doesn't have any control points. So you can pretend that this control point just collapsed into the point here. So I got rid of the control point. So there is still a control point here. It's still a cubic Bezier curve, but this control point was just moved to be on top of the point in the line. And here I can say that this is something called a smooth point. So now this node is called a smooth node. So these are still Bezier curves, cubic Bezier curves. I'm not changing them to be quadratic. I'm not changing the nature of the curves. I'm just changing how the control points behave in relation to the point that they attach to. So now the smooth curve has the property that when I move it around, the other one moves to compensate. Cool stuff, huh?
Very cool.
And then there is this, which is called an symmetric. So this time when I move one around, the other one moves too. But you can see that here I can make one of these lines between the actual point and the control point. I can make one of these long and the other short, while in this symmetric case I cannot. They move in terms of distance together as well. And then there is this
like two kinds of symmetry.
Yeah. And then there is this other one called auto smooth, and I believe the auto smooth one is the algorithm we are going to implement.
Nice.
Because what that does is, I don't know, we'll see, but I think that if I select all the nodes and make them straight lines, so now these are straight lines, they are a polyline, and now that I say this, do you think that Inkscape implements this as a polyline, or do you think that it implements it as a path?
I don't know that there's any advantage to polyline, so probably a path.
Yeah, I think it does it with a path. But it does not use the C command in the path. So M is for move the cursor, but then it does not use a C, so it's drawing straight lines. But it's using a path, not a polyline. So if I select all these points on my line and I click on auto smooth, then it does something. It makes the line smooth. That's exactly what we are about to implement. And it does so with the kind of node that is smooth but not symmetric. So this one. So this one means that I can have a control point that is longer and another one that is shorter, but I cannot just move the control points independently of one another. So the algorithm on this page and the algorithm that we are going to implement is this one for auto smoothing.
Okay.
And okay, so what makes we are interested in making things smooth. We are not interested in this, right? So why are we not interested in this? Well, because it doesn't look smooth, even if I make this not be exactly straight. So this is not exactly straight, and that one is not exactly straight. But you can see there is a sharp corner here. And that we don't want. We want the corners to be all smooth. I think the result will look better.
Yeah.
And Inkscape seems to agree with me.
I think that's the primary thing that we want.
Yeah.
Actually.
So in order to make that happen, the thing is these two control points need to form this blue line. It needs to be a straight line. So that is the property of this so-called smooth point. The line is straight. That's why when I move one of the points, the other one moves accordingly, so that the line keeps straight. So you can see that if I make the line straight, it doesn't really matter how I move, there is no sharp corner. See, it's not sharp, it's smooth. And if the lines, this blue line and that blue line, if they are relatively the same length, then this this curve is about as curvy as this curve. But if I make them very different, like so, then this curve is very curvy, and this curve is not as curvy, but it's still not a sharp corner. It's still smooth.
Just about.
Yeah, barely smooth. In fact, if I make this control point be so short, it is still going to be... let me make it as close as I can. So it's still going to be... Oh, I got it wrong. It's still going to be a straight line. This blue line is still going to be a straight line, but it's very close to the point, and it almost looks sharp. It isn't really. It is a smooth corner. There is a curve to it. When I zoom in, you can see there is a bit of a curve, but it's very sharp. Okay, so how do we do the auto smoothing? Well, you can see that when this point is auto smoothing, I can change these other points around, and the auto smoothing will continue to happen. Inkscape is smart enough to compute these points for us. And unfortunately, that is Inkscape being smart, because if I look at the source, there is no magical parameter for me to say I want the curve to be auto smoothed. No, it is computing these points, and when I change the points around, the coordinates here change as well. So this is
starting to get an idea for how this might work now.
Yeah, we can even maybe put the points in particular places, and then we can, at the end, when we have our algorithm implemented, we will be able to compare results. And I'm not sure that Inkscape is using the algorithm we are going to use, but I guess it is. Just a guess. But you can see that these points are being moved around, and the control points here are being moved around as well. So Inkscape is being smart and recomputing the algorithm we are about to implement. Unfortunately, it's not baked into SVGs. And another thing to note is that an auto smooth point is represented with a circle. But when I move one of these handles around, it can no longer be an auto smooth point because I am changing the control point by hand. So it turns into the square, which is a smooth point. Okay, so let's make this auto smooth and play around with some of the handles. So I guess I will make this relatively smaller, like so.
So is the gradient... What I was thinking initially is if we name those points A, B, and C, I was thinking that the gradient of the line should be parallel to the gradient of the control points, but it doesn't look like between A and C.
Yeah, so I am putting A, B, and C here on the screen, and your intuition is exactly right. It may not look like that. You are saying, cool. But I don't know why it doesn't seem like that, but your intuition is exactly right. So the first property we want from this control line, these control points, is that we want this line, this blue line, to be parallel to a line that would appear between A and C. And it may not look like that because of...
Well, it does a bit more now.
Well, maybe it's an optical illusion. Maybe Inkscape is not using the same algorithm we are going to use. We'll see. In fact, we can first of all, I think we should make these two other points be cusps like these, or maybe auto smooth as well.
You could verify that.
Yeah, so that's what I'm
verify
gonna
that
do
now.
right now. So I'm making all the points auto smooth, so there is no weird handle here to throw things off. And let's see if Inkscape is going to use the same algorithm we are going to use. And to do that, I want to draw a line between if I do it like this, I think that it will add this line to the existing drawing. No. So I can take this line and I can move it around. And I can put it about here, which will be over point B. So it's not parallel. So our algorithm will not be the same as the one in Inkscape, because our algorithm will make these two lines parallel. And just by looking at this, it seems like it is okay. It is still a smooth curve. Maybe not the same smooth curve that Inkscape would give us, but it's still smooth.
Yeah, Inkscape might not be optimized for drawings anyway. It's optimized for, I guess, symmetrical smoothness. But I don't know.
Well, Inkscape is designed to
It
draw.
looks like Inkscape takes the length of the segment into account as well.
Yeah, and that's another thing we want to do. So if this point is closer to this one, then we want this control handle to be shorter. And that will make points that are closer together, they are able to make sharp turns. So that is when you're drawing slowly, and then we have more points to work with, so it's okay for the curve to be sharper, because the points are closer together anyway. But when points are further apart, so maybe you are moving your hand in the drawing very fast, and we cannot collect enough points, then the handle needs to be longer, like this, which will make the curve smoother. Okay, so let's talk about the algorithm here. We want to make it so that this line will be parallel to this line, so the angle here will be the same. And we want this handle to be proportional to this line, and we want this handle to be proportional to this line, or actually to the distance between points A and B and points B and C. And also, we want something that I think we can call the smoothness factor. And this is something that I think we will find a couple that work well, and maybe we will present this to the user. Maybe the user will want more smoothness or less. We'll see if it makes sense to present this to the user as a parameter that they can change. But what the smoothness factor does is determine how long these lines will be. So we already know that this line needs to be shorter than this one. So maybe if this point is half the distance to this point when compared to B and C, so if the length of AB is half the length of BC, we want this to be half the length of that. But, okay, we have a ratio, but we don't have a length. So the length will be determined by this T factor, this smoothness factor, which is usually called T. It's called T in this document. So we want the T to determine the length of these things. So we have a proportion. This will be half the length of that. T will say if this is like the thing that I had before or something more like this. So you can see that the bigger the T, the longer these lines and the smoother the drawing.
My first thought is you might not want that factor to be just a factor, just linear. You might want it to have some, a non-linear proportionality to the length of each segment.
Maybe so. So lines that are closer together will have smaller segments, and lines that are further apart will have even bigger segments. Yeah, that is a possibility. Haven't thought of that. But you can see that the bigger the T, so the bigger this smoothing factor is, the more the line will be curvy, up to a point that the smoothness factor is so big that we start to draw some loops. I mean, you can imagine that I can continue this drawing with some more points. like this, and if I make these segments also be, let's make them auto smooth, and now we can just move this these handles around, and we'll make the control point so large that you can start to see some loops. I don't think we want that for our drawing app, but it's just a cool property of the algorithm. Okay, so here in this document there is a very nice drawing of the situation we have. And it also has an implementation of the algorithm which happens to be in JavaScript. Cool stuff, right?
That's useful.
Yeah, it's not bad. So how do we compute these points? Let's look at this drawing, because this drawing is the key for understanding how the mathematics of this will work. So points x0, x1, and x2 are our points ABC from before. These are the points we collected from your mouse. And we don't have a curve yet. We are about to compute the handles for drawing the curve. So the way that this works is, first you have to compute the distances between x0, x1, and x1, x2. We'll need
Makes
that.
sense.
Yeah, we'll need that to compute the proportion between the distances between x1 and the respective control points. By the way, the control points that we are going to compute are p1 and p2. So we will need these distances. Also, we want this line, which is the line that is the blue line in Inkscape, the line between the control points. We want this to be a straight line, because we don't want an edge, a pointy edge here. And we want P1 and P2, the line between P1 and P2, to be parallel to the line between x0 and x2.
Yeah.
Also, we want these triangles to be proportional. So this triangle is the triangle T, determined by points x0 and x2. And it's a right triangle, so that's why you can define the triangle with just 2 points.
Right angle triangle, yeah.
Yeah. So there is this right angle here, and we want this triangle to be proportional to these 2 triangles. And this has the effect of making the proportion between P1, X1 and X1, P2. These 2 proportions will follow the distances, because T is proportional to TA and TB. So the thing I like about this algorithm is that it has this figure, this geometric intuition. We are not talking about doing manipulations of matrices. No, we can see the algorithm right here. And unfortunately, in this drawing, it seems like TA is similar in size to TB. It is smaller, but not by much. But that's because x0, x1 is different from x1, x2, but not by much. This line is about the same size as this one.
Makes sense.
The more drastic the difference between x0, x1, and x1, x2, the more drastic the difference between TA and TB, and the more drastic the difference between P1, x1, and x1, P2.
This is really cool.
Yeah.
I like this. Yeah, it's cool.
Yeah, so how about we don't take a peek at the JavaScript implementation and start implementing our own?
Let's do it.
So we know that we will want to iterate on this over time and iterate over all the points. But never mind that. Let's start with something simple. Let's go to our drawing canvas, and here in the SVG, we have a drawing, and we can just start adding stuff to the drawing by hand, so we can test that this will work. So let's say drawing.insert adjacent HTML, and we'll do that after or before end. It doesn't really matter because the SVG is empty, but so before the end, we will add one of those path SVG elements, and we need some stroke properties so that we can actually see the path. So we want the stroke for this example to be Crimson was your favorite color last time. The stroke width, let's make this...
Good memory.
Let's make this relatively thick, and we don't need to change the opacity, and this won't hurt. But then we have our D. So with D, we can... Let's go back to the MDN docs for path. So let's try to find an example for a cubic Bezier curve that maybe we can copy and paste. I can see that you are already busy and you are starting to draw to implement some things, but I am just copying and pasting stuff.
No, yeah, it makes sense.
Okay, so here is the example I copy and pasted from MDN. And let's see how this looks, and we'll try to make sense of what's going on. So here is our curve. It kind of looks like the curve here in this example, in its shape. There is also a black line, and I don't know what that is all about. But let's make sense of what this even means. So the way this works is, first of all, in every path, you need to move your cursor to the starting point. Our starting point is coordinates 10 and 90, which is up here on the top left of my screen. So to make this be more centered, I will make this maybe something like this. So it will move to point 100 and 300. It will be like about here. And then C is the command to start drawing a cubic Bezier curve. And then we need to give it 3 arguments. And in MDN, they were using commas differently. And when you are using these coordinates in SVGs, it doesn't really matter if you put commas everywhere, if you put spaces everywhere, if you don't put spaces. And it seems like MDN is following a different convention. My convention is to use coordinate pairs separated by space and then different points to be separated with commas.
Oh, okay. It's quite random though. It's quite tolerant then.
Yes, it is. And the reason why I do it this way is so that I can split on the commas, because spaces appear everywhere, right? Here there is a bunch of spaces, but commas separate coordinates.
Yeah,
so I can separate the commas, and then I can just trim everything and get rid of spaces and then separate by space. In fact, that's what we are doing in the eraser right here. We are splitting on the comma, and then we are taking out the spaces and splitting on the spaces. Or we are taking out the spaces from the left and right. So if you end up with something like this, I will trim out this first space, and then I split on the space. Okay, so we have this, and now let's look at these 3 points. They are 3 coordinates. This is... Okay, this drawing got complicated. Let me get rid of everything and start over. So we already gave the SVG the first point. We moved our cursor here. And then I'm actually going to delete this segment. I'm going to have just a single segment because that's what we are drawing. We are drawing a single segment. So we already gave Inkscape this point. We already gave the SVG this point. And then we need to give the SVG this, that, and the other one. And we give them, we give these points in this order. So we give first this point, then that one, and then that one.
Yeah. Okay.
So how about we try to mimic this curve by hand? So we are on point 100, 300, and this will be way up there and more to the right. So how about this becomes point maybe 120 and then 400.
Yeah.
this will be even more to the right. So how about we say that this is 200, and then it's slightly lower. So let's say that this is 390, and then
I guess
this.
I'm not sure how we're going to. Yeah, go on. Sorry, go ahead. Keep going.
You can ask.
Well, I'm not really sure how we're going to handle points less than 2. I guess we'll just, if it's multiples of 3, then we can apply our cubic algorithm, and otherwise we just draw a line.
I think that what we can do to handle the case, we have to handle the case regardless of whether it's even or odd. And now we are talking about the thing we are going to do later. When we have the algorithm for a segment, we'll do it for a whole bunch of lines. But I think that the way it works is you have to handle the first and the last one, because remember, our algorithm can only work with lines that look like this, because it will compute the control points for this guy here. So how do we handle the first and the last one? I think that what we do is we duplicate this point and we duplicate this point.
Okay.
I think that's how we handle that, but we'll have to see. In any case, we are here.
That's quite an elegant solution, yeah.
So we are here, and we now need to give the coordinates for this last point. So this last one is way further on the x-axis. So let's say that this is 300, and it is higher than this one, which is 300, but it's lower than this one, which is 390. So let's say that this is 320. And now let's see what this looks like. Okay, so it is upside down because I was thinking in coordinates in terms of this being 0 and then numbers would increase this way, but it actually works the other way around. And the reason why there was a black line before is that there is a black fill to the path by default. So we can say that the fill should be none, and then we should get rid of that black portion.
Makes sense.
Okay, cool stuff. So I had the coordinates upside down, but other than that, the shape is similar to the Inkscape thing. And I guess you have to leave now, right?
Very soon, yeah.
Okay, so I'm going to continue until 8 p.m. on my time zone, which is 7 p.m. on UTC, but you can leave whenever you want.
Okay. I'll hang out for a little bit longer.
Okay, so now the algorithm we want is going to receive as inputs these 2 points. These are the points that we actually collected from the mouse. And these 2 points are the outputs, the control points we want to compute. So how about we say that this is the points, and then we have maybe this and that. Or maybe we can just have them as arrays. Yeah, that's simpler. And we want to compute our control points. And in this case, it will not be this. I came up with these values out of nowhere, but the result will be two numbers like this. Okay, so how do we do this algorithm? It is the algorithm over here, right? This figure, and also this code, but don't look at it. So it is this figure. So how about we open the figure on a new tab? This way we are not tempted to look at the implementation. So one thing I know that I will need this distance between x0, x1, and x1, x2. So, oh, yeah, right. My algorithm does not receive 2 points as arguments, it receives 3. So how about we put another point here? Let's say this is point 200, 400.
Mm-hmm.
And I guess we can give these guys the same names we find on this figure to make things easier to see the relationship. So I'll put this code on the left and our figure here below our heads. So x0 is this, x1 is that, and x2 is this. Now, we know that we will need the distance between x0, x1, and the distance between x1, x2. And we have computed the distance before when we were doing the eraser, because we wanted to know if the eraser was close enough to one of the points in the figure so that it could remove the figure. And this was the formula for computing the distance. And if you're interested in learning how this formula works, then go watch my previous stream on Monday, or maybe Friday, I forget. But that's the formula. And here we need to say what are the x coordinates of x0, x1. So let's say that this is x0, x1. Or maybe the distance x0, x1. And here we say x0 at position 0, which is our x. Okay, so maybe at this point, since I'm talking about x and y, it may be better for me to move, to change this arrangement so that it is an object. Oh, come on. Like so. So now we can talk about x0, x. And it's so unfortunate that these points are called x because x is also the coordinate, x and y. But in any case, x0, x minus x1, x. And here x1, y, and x1, x0, y, and x1, y. So that's our distance between points 0 and 1. And I guess I will comment out this line so we can run the formatter for this. Oh, the formatter.
Maybe you should call the. Yeah, it is confusing having x0, 1, and 2. Maybe call them A, B, and C.
Yeah, but the figure here says x0, x1, and x2. So it's kind of confusing to read it like this. And in the end, I think we will rename our stuff. But for now, that we can have this relationship, we'll do it like this. And now the distance between x1 and x2, that's easy enough. We can change the x0s to x1s and the x1s to x2s. So now we have these distances. Now, we are interested in computing. Oh, and we'll also need the smoothness factor. So I'll say that the smoothness factor starts with 0.25. I came up with this number on the spot, but the article also recommends numbers between 0.2 and 0.5. We'll play around with this. So now we have these distances, and we have x1, and we want to find, for instance, p1. Okay, so p1 will be a point based on x1, so its x position will be based on x1, but we need to go to the left. How much do we need to go to the left? Oh, I guess we need to compute the height and the width as well. So let's pause for a moment and compute that. So the height is x2. Let's compute the width first. So the width, w here, is x2 x minus x0 x. So we are getting the x position of this guy and that guy, subtracting, and we get w. And similarly for the height, we do that with y this time. Okay, so now let's come back. We want to compute p1. So p1, its x position is based on x1, but we need to go to the left so we can subtract. And what do we subtract? Well, it's a proportion of w, right? We want to subtract something that is proportional to w because these three triangles are proportional. So we'll say w and we'll multiply by a factor. One of the things is the smoothness factor, because the smoothness factor will determine this distance. But we also need to multiply by the proportion between the lines, right? So we have a proportion between x0, the distance between x0 and x1, and the distance between x1 and x2. So let's calculate this proportion. So let's say that this is the ratio between this and that. My naming convention is all over the place here. But that's simple. It's just a simple division. It's a ratio. So now we have the ratio, and I guess we don't want the ratio. We don't necessarily want the ratio between this and that. We want the ratio between this and the whole way around. So let's have another one that is the distance between x0 and x2 following this line. So it's not the distance following this line. So I guess it's the distance between x0, x1, and x2. So that one is simple. We can just add up this distance that we have computed and that distance that we also have computed. So we can do it like this. And now the ratio between this distance x0, x1, and that. So that is this distance divided by that. And similarly for this. So now we'll have that. Yeah. So now we have this weirdly named variable is the ratio between this distance and this distance. If I copy and pasted everything correctly. And this weirdly named variable is the ratio between this distance and this distance. So now we can just take this ratio and multiply. So we know that we want to go to the left of x1, an amount that is determined by the smoothness factor, but also determined by the ratio between x0 and x1 and the whole distance. So this line will be shorter if these 2 points are closer together. All right, so now let's do the same for y. Or for y. So now we are still looking at P1, but now we are looking at the y coordinate. So this time it is still based, and I should have said that this is based on x1, x. So it's still based on x1, y this time. It's still based on x1. And now we are not looking at the width because we are on the y-axis, so we are looking at the height, and we still multiply by the smoothness factor, and we still multiply by this distance because we are still talking about P1. And that is our P1, our lovely P1. Let's do the same for P2. So this time it's still based on x1, but now we are, and it's still looking at the width and the height, just the same, but now it is looking at the ratio distance based on x1, x2, so this line. So let's use that variable instead. And now we are to the right of x1, so we don't subtract, we add. And P1 and P2 are our control points. So now let's draw a figure that is, first of all, right here, it will be x0, x0, and here we'll get the x and y coordinates of x0, and here we'll put x2, the x and y coordinates of x2. And then on these two positions, we'll plug in P1 and P2.
This is the moment of truth.
Let's hope for the best. And there you go. We have 3 points and it forms a curve.
Nice.
Now, I would like to see the points as well as the curve, so I can quickly come here and draw a circle such that the center of the circle on the x-axis will be this, and the center of the circle on the y-axis will be that. The radius of the circle will be 3, and the fill of the circle will be blue. Let's see if we see a point. And we do. The point is right there. So now let's make this slightly bigger and copy and paste this 3 times. So we see x0, x1, and x2. Okay, so these are the 3 points we have collected, right? Did I copy and paste everything correctly? x0, x1, and x2. And this is the curve we ended up with. So it is not correct.
Yeah.
There is some mistake somewhere. Let's also look at the control points.
Yeah, yeah.
So the control points will be in purple. And there are only 2 of them. And they are called P1 and P2. And here are our control points.
Interesting. That's kind of what we hoped for.
Oh, I think I made a mistake because we are moving the cursor to point x0 and then we are drawing up to point x2. But no, we just computed P1 is a handle on one side and P2 is a handle on the other side. So yeah, we need to draw 2 segments, not just one.
Yeah.
So let's do it like this. I'll copy and paste. And I don't think I need the second C there. So we'll draw a segment between x0 and x1, and then another segment up to x2. And P1 is the control point to the left of P1, and P2 is the control point to the right of P2. And here, I don't know what to give to this other control point, so how about I just give x0, and here I can give x2. So the control point will be on top of the point on the line, which makes it like one of those cusp points. Is that how it was called? Corner points. So we will make this a corner point because we will take the handle and just collapse it on top of the point. So now let's take a look at this.
But you will eventually.
There you go. So
Nice.
now the smoothness factor is maybe too small because this curve is not too curvy.
Yeah.
So how about we just come here and make it smoother by saying that the smoothness factor is 1/2. There you go. So now the line is going through the points correctly and the control points seem fine and it seems curvy. So all we have to do is iterate on this to compute the rest of the lines, the rest of the control points.
Seems like a great time for me to sign off. Congrats! It's a brilliant start.
Yeah, I guess, you know what? How about we just wrap this up? So yeah, we made some progress. We are going to commit whatever we have and push. And I know that this code kind of is just preliminary code, and we'll push this. Do you want to comment on the things that you wrote here? So yeah, this formula is the same we had.
Yeah, my thinking was my intuition would just be to like write a function for distance and for slope, and then I'll worry about the internals later, and I just have the sort of like the skeleton of how the algorithm works, and then fill it in afterwards. Which is why I started with distance and slope first. And I imagine you're using the distance in like 3 or 4 places, and I guess it's easy to have a typo in one of them. Yeah. So I would just create a function and reuse it.
Yeah, I tend to copy and paste stuff while I'm prototyping like this, so I don't have to think about I don't have to think about function extraction and whatnot. But this slope thing would compute this angle, right?
Yeah.
Yeah. So instead of trying to compute the angle, it would specifically compute this angle right here. But instead of computing the angle, I just used the property that these three triangles are proportional, and I used height and width to compute height and width of these two triangles. I guess, I guess that's the essence of this algorithm I just wrote. This whole shenanigans here is, this whole shenanigans is computing this part in particular. So we have the coordinate for x1, and we want to compute this distance here, and we do that with this line. So this line takes this width and multiplies by a bunch of things so that it computes this width. So I subtract and I get this x coordinate. And similarly for everywhere else.
Got it, yeah. Makes sense. Yeah, that's a nice way of doing it too.
Yeah, and this way I don't have to think about trigonometry all that much. Because when you insert angles into this story, you have to start thinking about tangents, sines, and cosines, and...
It would actually compute the gradient rather than the actual angle. So you don't actually... It would just be multiplying it out.
Oh, fair, yeah. Okay, so I think that's it for today. We are going to sign off now, and tomorrow I will be back here to implement the iteration that will collect all the points, and it will compute this algorithm for every point. So then I will extract some functions, I think, maybe. We'll see. But yeah, thanks for joining me, David. And
thank you for having me.
I hope you had fun. Thank you everyone who watched, and I see you tomorrow at 7:30. At 5:30 UTC for more of this. Bye.
Bye.